Hi everyone, my name is Vaidi and I'm an analytics specialist here at AWS. And today I have with me two esteemed customer speakers representing Twilio, Dhara Patel, Director of Engineering, and Rahul Chandel, Senior Engineering Manager. And together they will talk about how Twilio scaled its business intelligence with a data lake powered by AWS. The agenda for today is pretty simple. I'll start by quickly introducing the idea of a lakehouse architecture on AWS, and then I'll pass it to Dhara and Rahul, who will share how Twilio has used the guiding principles of that approach to build and scale their data platform. So let's get started. Our customers are taking all their data from various silos and integrating all of that data into one location for, of course, the purposes of analytics and machine learning, and many call this data repository a data lake. At other times, these same customers are using purpose-built data stores like a data warehouse to quickly analyze structured data for BI, or a search service to search and analyze log data to monitor the health of production systems. And as more and more customers use data lakes and purpose-built stores in conjunction with each other, we also see that they often need to move data between these systems. For example, you may want to collect web clickstream data from your applications directly in the data lake, and then move a portion of that data to a data warehouse for your daily reporting and dashboards. Now that is a move from a data lake to a purpose-built data store. You may also want to move region-wise product sales results from your data warehouse into your data lake to train product recommendation algorithms using machine learning. Now that is a move from a purpose-built data store to a data lake. Alternatively, you could have a product catalog data sitting in your database and you want to move it to a search service so you can easily search your product catalog. And that's a move between purpose-built data stores. To achieve this, customers are building modern data architectures that allows them to rapidly build a scalable data lake. This architecture uses a broad and deep collection of purpose-built services that provide the performance required for use cases like interactive dashboarding and log analytics. It helps them to easily move data between the data lake and those purpose-built data services. It helps them to set up governance and compliance in a unified way to secure, monitor, and manage access to that data. And it allows them to benefit from low cost without compromising performance and scale. Together, all of these facets come together to this architecture construct that we call a lakehouse. After all, it's not just about integrating your data lake and your data warehouse, but it's about connecting your lake, your warehouse, and other purpose-built data services into a coherent whole. So how do you implement a lakehouse architecture on AWS? It starts with Amazon S3. Customers have been building data lakes on S3 longer than any other cloud provider, and today more data lakes run on AWS than anywhere else. In addition to a data lake, customers use a combination of our purpose-built database and analytics services like Amazon EMR, Amazon Elasticsearch, and Amazon Redshift that match the right tool to the right job, delivering high performance and scale at the lowest possible cost. To move their data between these systems, they then use AWS Glue, our serverless data integration service. And finally, they use AWS Lake Formation to manage the security and governance of all that data, regardless of where it sits in the data lake or in purpose-built stores. And in all these cases, we've invested heavily in offering the best price per unit of performance. So with that, I will now send this to Dhara and Rahul to tell you how Twilio used the lakehouse approach to build and scale their data platform.
Thank you, Vaidi, for the introduction. So before we dive into the data lake and its ecosystem, let's first start with what is Twilio. So Twilio is the world's leading customer engagement platform that lets you build differentiated experiences for your customers across your entire business at any scale. It is a fully programmable platform that allows you to use any API or a service to build your engagement solutions so that you can reach your customers anywhere at any time. To today it is used by over 8 million developers worldwide that has built engagement solutions that power over 190,000 businesses, reaching their customers in over 100 countries across the globe. So now let's talk about how we use data at Twilio. At Twilio, we have a culture of wearing customers' shoes. Now, in order to do that, we need to better understand our customers and their interactions on our platform. For that, we need a data backbone that enables the data-driven decision making in a self-service manner. So let's talk about some of the use cases that is supported through this data backbone. The first one is customer segmentation. We use data to segment our customers so that we can help them build the right use cases using right tools. The second one is the customer loyalty. It really comes from personalized communications. We use contextual data about our customers to generate personalized messages that are a lot more appealing for our customers. Third is effective funnels. We use data-driven insights throughout the various stages of funnels, whether it's lead generation or nurturing or sales engagement, to increase the conversion rates throughout our funnels. Intelligent services. We use data-driven intelligence to resolve for customer inquiries in an automated fashion so that we can reduce the time to resolution and overall cost of contact. Financial efficiency. We use metrics, measures, and advanced modeling techniques to find better investment opportunities and profitability for future. And lastly, workplace efficiency. At Twilio, we rely on data to create healthy and efficient work culture. Now, all of these use cases are supported through a strong foundation of a data lake ecosystem, which is what we are going to talk about today. But before we go there, let's first talk about the data lake and what is a data lake. So a data lake is a central repository of all data, whether it's structured or unstructured, which is securely stored, governed, and shared across the organization at any scale. Now, in order to design such a central repository or a data lake, we follow certain guiding principles that helps us design our data lake. So let's go through our principles. The first principle that we use is keep it simple. What it really means is that we want to design an architecture which is a set of cohesive, simple services that are designed to do maybe one thing, but it does it well. So when I personally think about this principle, I think about a dish of ravioli, where it is very nicely created and the architecture looks very neat and clean with a simple services, because the key here is simplicity. The second principle that we follow is own your data. Now, later in this session, you will learn that the data is generated in a lot of different systems. It goes through a lot of different processes and being stored at various places. So at the end, when we create this centralized repository, we want to have control over our own data so that we can evolve our technologies, our data sets, everything based on our business needs that changes over a period of time. So at the end, we want to have a control of our data, which is captured in this central repository. The third principle that we use is an open format. What it means is that we want to store all of this data in an open format so that we can easily lift and shift with different technologies and systems as the industry evolves and also as our business evolves. Another advantage of using an open format is that we can also allow our consumers to bring their choice of tools to consume our data. The fourth principle that we use is the lakehouse architecture. This is really where we create multiple houses, which is nothing but the different use cases that are supported through a single foundation of a one data lake. And we will see all of these principles on how we have applied while we have built our data lake ecosystem. So let's talk about the data lake ecosystem. Now, data lake ecosystem is a collection of infrastructure and services that forms the data backbone. There are three primary stages of building the data lake ecosystem. The first stage is the data arrival stage. In this stage, the goal really is to make all the data available in the data lake. The second stage is the data residency. The goal here is to make all the data accessible for all of the various use cases that can be supported through this ecosystem. And the third stage is the data consumption. This is where the focus is on making the data usable for all of our users in a self-service manner. So now let's look at each of these stages in detail. The stage 1 is data arrival. Now the very first step in this stage is to identify the data sources. Typically in any company there are two types of data sources, first party and third party. The first party data sources are the systems that are owned by Twilio, like our product systems. On the other hand, the third party data sources are the applications that are used across the business but are not owned by Twilio. And some of the examples of this kind of data sources are Salesforce or Zendesk or Jira. Now, each of these kind of data sources has a lot of important information or data that is generated or stored in these systems. So how do we make this data available in our data lake? For first party, we use the Kafka-based data pipeline to route the data to our systems. For third party, we have developed a set of integration processes that extracts the data from these third-party systems and brings it to our data lake ecosystem. Now, both of these processes load the data first into a staging area. Now, this staging area is powered by AWS S3. At this point, we collect all of the data from these various data sources and apply certain basic checks and certain basic optimizations and really prepare the data for further loading. This is where our loaders kick in. So loaders are nothing but these are a set of processes that parallelly loads all of the data from the staging area to our data lake storage system. We use event-driven mechanism to generate and to constantly look into our staging area where as soon as the new data arrives, it triggers our loading processes that takes the data, applies optimizations, and loads it into our data lake storage system. We use SNS and SQS for our event-driven mechanism. Our loading processes are really powered by Spark, which is all deployed on various EC2 machines. And we use Elastic Cache for the state management and really managing all of this parallel processing of a lot of this data. Before we load the data, we apply certain standardizations, optimizations, partitioning schemes, etc. to really optimize the data that is then captured in our data lake storage system. Our data lake storage is also powered by AWS S3. And here the data is stored in a fully optimized fashion so that it can be used for analytics and reporting for business needs. And so now at this point, we can say that we have made all of the data available in our data lake storage system. Now, remember we talked about all of these various guiding principles that we follow in designing our data lake. So here I would like to highlight that we have up in this stage, we have applied our principle first and second, which is keep it simple and own your data while building this stage. Now, the reason it's a simplified architecture is because we have created an independent services for first-party data processing or third-party data processing as well as the loading the data. Each of these are independent services which makes this architecture a bit simpler. Similarly, as we have talked about that data is generated in a lot of different systems, we have stored all of this data into a one single data lake storage system, which is fully owned by us. so that we can apply optimizations or any other standardizations as our business needs arises. All right, so let's move on to our second stage. The second stage is about data residency. So at this point, we have all of our data captured in our data lake storage system. So now how do we make this data accessible for various use cases? There are three primary use cases that we support: warehousing, data science, and exploration. Let's look at each of them. For warehousing, the most essential step in the process is the data transformations. We apply highly custom business logic to create the curated data sets for business needs. Presto is our transformation engine. So what it does is that it reads all the raw data from our data lake storage system and then apply all the SQL-based transformations, create the transformed data sets, and then store them back into our data lake storage system. And then eventually our loaders take this data and then load it into Amazon Redshift, which is our data warehouse platform. Redshift powers all of our reporting and analytics use cases using all of the highly transformed data sets which are stored in Amazon Redshift. For data science, we use Spark to generate all the data science models. Here also, we create all the data sets using the data science models and put it back into AWS S3, which is then loaded into a dedicated data science clusters, which are also powered by Amazon Redshift. For exploration, we provision dedicated Presto clusters for the teams and give them SQL capabilities to access all the data that is stored in our data lake storage system. Whether the data is raw, transformed, or it's a data science model, all of these data sets are fully accessible for exploration via various Presto clusters throughout the data lake compute system. So with all of these capabilities, we can say that we have completed our data lake with the storage and compute capabilities. Now here in this stage, we have applied our guiding principle number 3 and 4. So our third principle is about storing the data in open format. So here all of the data that we have stored in our data lake storage system is in open file formats like Parquet, Avro, or JSON, which has actually made it possible for us to use a lot of these different technologies like Presto, Spark, Redshift, etc. Similarly, the fourth principle is basically our lakehouse architecture. So here, all of these three use cases, warehousing, data science, exploration, are really the houses that are built on a strong foundation of a data lake storage system, which is powered by S3. So now let's move on to our stage number 3, which is the data consumption. Now at this point, we have our complete data lake with the storage and compute layers built up. So now it's time to consume the data. We use Looker and Tableau for reporting and analytics. Our users can use any of these tools to connect to any of the compute systems, whether it's Redshift or Presto, to generate their insights and generate their analysis. So at this point, we must think that our users have been able to consume all the data through their choice of tools, right? But remember, one of the things that we wanted to do was to make the data usable in a self-service manner. So how do we achieve the self-service? So for self-service, the very first thing to do is to create the user access a self-service. For that, we have created our automated Slack bot, which actually automates all of the provisioning and deprovisioning of access, including generating the approvals and really allowing our users to get their access without talking to a single human. One of the big things in any self-service environment is the data catalog. We have created a central data catalog with a lot of rich metadata for all of our data sets. A lot of this metadata is about business descriptions or schema information or data classifications, as well as the data loading and data quality status. So all of this rich metadata is captured in a central meta store, which is also searchable via an easy to use self-service portal. Our users can browse through a lot of this rich metadata and get the answers that they are looking for using an easy to use self-service environment. In addition, our self-service environment also allows users to subscribe to their favorite datasets. And they can also get notified on any changes to their favorite datasets. One other big aspect of self-service is data education. We have created various how-to articles and self-guided videos as well as training programs to educate our users on our systems, our processes, and our data sets so that they can truly self-serve their data needs. In addition, we have also created a certification program where users can go through a certification and become power users on our platform, where they can not only just use all the insights, but they can also publish the insights and analysis for broader consumption. So we have used lots of various technologies to build this entire self-service experience. So we use Elasticsearch for our search use case. We have developed web services using Scala and Akka, which allows to interact with our self-service environment as well as our central meta store. We have used Cassandra to power our central meta store, and then React is used to create our in-house self-service web portal. So now at this point, we can truly say that we have enabled data-driven decision-making in a self-service fashion. So now let's quickly put everything together. In our data lake ecosystem, the data moves from the very left end of the systems where it is being generated to all the way to the right, where the data is consumed by our users in a self-service fashion by going through the various stages of forming the data lake ecosystem. And this is how our data lake ecosystem is the data backbone, enabling the data-driven decision-making in a self-service manner. So now I would like to hand it over to my colleague Rahul, where he will talk about the data lake excellence.
Before we go into the details, let's first talk about what is data lake excellence. It is a way to measure the success of our lake against the set of benchmarks that we have established. Creating a data lake isn't enough and doesn't guarantee success. We have to take extra measures to make it architecturally, operationally, and financially successful. Let's start with the architectural pillars of our data lake excellence. There are 4 main pillars which we have used as a base to support our data lake. They are cost efficiency, performance, reliability, and compliance. All of them are equally important, and the lake needs to be performant in each of these parameters. Let's talk about the pillars and a set of operational metrics that will help us measure and make our lake a success. Imagine a scenario where you have terabytes of data coming in every day. How do you know you're spending enough and not over on storage cost? You need to optimize for both storage as well as for processing. Well, there are certain basic things that you can do to optimize for cost, like choosing the correct file type for compression, for storage which can be accessed with minimal effort, like we use Parquet with Snappy on RS3, and we also optimize loads by choosing the correct column encoding while loading the same in Redshift. You can also improve efficiency by adding a lifecycle policy on the data lake. For example, not spending on cold data or data that is not used very frequently and moving it to Glacier. You can also use intelligent tiering to move unused historical datasets with proper planning, to move only selected prefixes which don't offset the monitoring fee. For compute, you can select the correct EC2 instance types for running your Spark and Presto based applications. We use R5 8x large, which has a good blend of both CPU and memory for Presto, and use R5 4x large for big Spark applications. We do in-house auto scaling and descaling for all Presto and Spark clusters to reduce cost during minimal usage time like weekends and after hours, and scaling up during peak times and office hours. You can realize an immediate value by moving the ETL jobs off of the expensive warehouse to the data lake. Optimizing and tuning the Spark jobs also helps in reducing the overall uptime of the instances. Now let's move on to our next pillar. As our data passes through SNS, SQS into S3 and finally to Redshift and Presto, it's important to identify where the bottlenecks could be. It could be while consuming thousands of messages or while creating the files, or it could be even while querying the data. Well, we have created work-based queues which has helped us to distribute the memory based on timings as the ETLs complete during off-business hours. Optimization of JVM and a reserved memory allocation for bigger queries along with query max memory and query max memory per node play a significant role in optimizing one's cluster and should be done carefully based on the use case. Proper partitioning and bucketing of datasets also adds a lot of value which are queried through data lake and optimizes the overall data fetch. We also have dedicated clusters for managing and isolating workloads across all of our services, and they scale independently. We have different clusters for running our daily ETLs for warehouse, internal teams, and for running large workloads, and a separate for our day-to-day operations for everyone else. We have automated dashboards and metrics which capture the bottleneck and autoscale our clusters based on certain thresholds like execution time of queries, number of services waiting in the queue to be executed, CPU and memory above a certain threshold, and number of queries that are waiting in queue for a certain amount of time. Caching results of small queries and data also goes a long way in optimizing and improving system performance. We use concurrency scaling features in Redshift by applying query CPU time and query queue time through our WLM configuration when we need to process an increase in concurrent read queries. For Presto, join reordering, use of group by instead of distinct, and use of partition columns in incremental tables while querying are also some of the basic things that make a significant contribution to the overall query experience. Identifying and capturing queries running for more than a certain time and creating a feedback loop with customers to optimize them also goes a long way in the overall performance of the cluster. Now, we know that our systems are performing, so let's talk about our third pillar, reliability. Now you have scaled your cluster and are cost efficient, but how do you ensure that your data lake is reliable? It is not only about storing multiple copies of data, but also about getting the correct data in the correct time. We have health monitoring and alerting across all of our services, which helps us to maintain correct backups and infrastructure in place in case our systems go down. We have self-healing for stateless systems, which are monitored through various self-health checks running on our instances like number of processes, memory usage, and space monitoring. And they alert us in case they cross the threshold and SLA defined by us and require action to maintain our infrastructure up and running at all times. It's important to ensure that the data that you're receiving from the source doesn't change or gets lost while it's consumed by the target systems, even if transformations are applied. To ensure completeness of data, we have custom health checks in place like last refresh time for a table, counts on a daily basis, custom null checks for selected important columns which inform us of any problems in our data. Defining thresholds for every dataset to check over a historical period of time is also a good way to ensure that your data is coming in a consistent way. It's also important to create modular systems so it's easier to recover using corrective actions. For example, to retrigger a data load if the source systems are missing data. So now we have talked about reliability, and finally, let's move on to our next and final pillar, compliance. How do we know if we are following correct standards for our data lake? Is the data lake in compliance with regulations like GDPR, HIPAA, or SOX? Well, we follow certain guidelines that we have in place and ensure that our lake is organized and managed in such a way to meet certain rules along with legal and governmental regulations. Let me share some of the basic guidelines that we use. Following all the procedures while deploying our code like an automated deployment and code review process. Having proper data access policies in place and making it available to correct individuals and team having the correct trail of all request permissions. Having the correct SDLC policies in place. having correct logging infra in place and making it accessible in case we need to go back and reproduce a certain situation, proper review process before granting permissions to various datasets, correct security controls before adding a new first or third party source, and periodic reviews. Regulation of access to classified data in the proper way so that a trail can be established through which access was granted. Data retention and deletion in an automated way. Encryption of data at rest and in motion. And finally, having correct documentation of all policies and procedures and having proper enforcement of all the policies. These are some of the very important questions that one must ask and that must be answered before you call your data lake a secure lake. And don't forget to review your systems every quarter. Before we end the session, let's do a recap of everything that we have covered today. First, we spoke about the data backbone and why data is important at Twilio by talking about some of the use cases like customer segmentation, effective funnels, loyalty, and various efficiencies. Then we learned about what is a data lake and what are some of its characteristics. We also covered our guiding principles that define our data lake, which are keep it simple, own our data, open format, and lakehouse architecture. We then talked about data lake ecosystem and its three stages, which are arrival, residency, consumption, that make our data and how we enable our users to make data-driven decisions. And in the end, we covered our four pillars: efficiency, performance, reliability, and compliance, where we spoke about some of the examples and guidelines that we use that support, measure, and make our data lake a success. We hope this session was helpful and you were able to learn more about our data lake and related practices from our experience. Thank you.